Okay, so finally we can get started. So today's topic is called MCF duality. So here the term MCF, it means minimum cost flow. I think you have already encountered this terminology in the lecture. So minimum cost flow model. It is something like, so suppose you have a network, just a demo. You have some network, and for every arc, you have a lower bound, say this is I, this is J, you have lower bound Lij, that's equal to some outer bound Uij. And for every arc, you also have some cost, which is Cij. That's to say, for one unit of flow on the arc Ij, the cost is Cij. And for every node, you have some balance called Bij. So remember that balance equals to out minus in. So the minimum cost flow problem is to find a feasible flow such that I say feasible because each xij should satisfy the lower bound and upper bound, and also for every node you should satisfy the balance condition. And we want to minimize the cost. This is called the minimum cost flow model, and it is widely used in supply chain logistics. And if we write it formally, MCF is something like we want to minimize Zx. So our x is our decision variable. That's the flow on each arc. Zx, this is equal to sigma ij in the arc set, xij times Cij. Remember that I said Cij is the cost of one unit flow from I to j. And the condition is, well, formally it says xij is greater than or equal to 0 and less than or equal to uij. So we can, in many cases, we can just assume that this Lij is 0. So xij should satisfy this for any ij in A. And also, j in out I, that's to say the outflow of I minus the inflow of I. This is equal to Bi for any I in N. Okay, so this is the formal definition of the minimum cost flow problem. And actually, many network problems can be regarded as minimum cost flow problems. For example, let's say shortest path problem. Actually, it can be transformed into this MCF problem. Or in other words, shortest path problem is a very special case of MCF. So in the shortest path problem, we are given some G, and we are also given starting position S and ending position T. And for every arc, say it has length, for every arc it is of unit length. Then how can we find the shortest path from S to T? So do you know how to transform to minimum cost flow model?
I would suppose we would set the cost just to be 1 for every arc.
Mm-hmm.
And we would want the balance constraints to be, I guess, for S it would be 1, for T it would be -1, and then for all the other ones it would be 0.
Yes. What else?
Xij would have to be between 0 and 1.
Well, actually, not necessarily. So you can just feel free to set Uij as positive infinity, because you have already said that Cij equals to 1,
oh, yeah.
and Ds equals to 1, Vt equals to -1. So Xij, the amount does not matter, because finally it should converge to 1.
Yeah.
Okay. Very correct. So this is for the shortest path problem. Then today, actually, what from this title, you see that we want to talk about the duality in the MCF. So let's first do a very quick review for duality. So for L duality for LP, linear programming. So recall that suppose the primal problem is maximize some C transpose X such that AX less than or equal to B, and X is non-negative. Then we have already said in one lecture before, the dual problem. I'm glad that you come. Okay. So today we'll talk about MCF duality. The MCF is minimum cost flow. This is the formal formulation of MCF. So now we are reviewing the duality for linear programming. So the dual problem is to minimize B transpose Y such that A transpose Y is greater than or equal to C and Y is greater than or equal to 0. This is what we have talked before in one section. So for this problem, please be very careful about the dimension. Let's say we have X in Rn. And A is in N and R. So that's to say A is an n by n matrix and B is in Rn. C is in Rn and our Y is in Rn. So be very careful about the definition. And also we know that for the duality, the original problem we call it the primal problem, and the other one is called the dual of it. So we know that in the primal problem, we need to decide what is the decision variable and what is the constraint. So I remember I have said this before. So in the primal problem, we have the decision variable. So correspondingly, in the dual problem, it corresponds to constraint. And for the constraint in the primal problem, actually it corresponds to the decision variable. Okay. Then fortunately, I have not erased this. So let's look at this MCF problem. What are the decision variables? And the color. So in the MCF problem, in the primal problem, the decision variable. The decision variable is arc flow, which is actually xij's. And constraints. Yeah, for these constraints, you should be very careful. What are the constraints? So we see that there are actually two sets of constraints. This is the first set. This is the second set. So for the first set of constraints, we see that it is about the bound for xij, the bound for the arc flow. And for the second set of constraints, it is about the balance of the nodes. So be very careful. In the MCF problems, the constraints are about both node balance and arc flow. Right, so be very careful. So what does this tell us? We see that the constraints are about both the node and arc, and the decision variable is only about arc flow. So that's to say, in the dual problem of MCF, at least when we are designing the decision variable, we should consider both the node and arc, not just for node. And the constraints should be about something about the arc flow, we'll say about the arc. All right. So this is what we do in the dual MCF. So in the dual MCF, let's first describe the decision variable. The decision variable, as we said before, because in the constraints of the primal problem, it is about both the node balance and arc flow. So in the dual MCF, the decision variable, we should form on node and arc. So for the node, in the textbook, we were introduced something about pi I. Pi I is called the node potential of I. So actually, I have looked up some materials online, and I was told that you can just interpret this node potential as something like the energy potential in physics. Right. So this is about the node potential, and for the arc, we introduced something called alpha ij. But unfortunately, I have not seen a formal name for this alpha ij, but let's just call it alpha. So alpha ij. And moreover, what can we say more about pi I and alpha ij? So pi I, because remember that in the dual problem, let me write it here so that to remind you something. So let's say in the primal problem, you are maximizing C transpose X such that AX is less than or equal to B with X non-negative. And the dual is to minimize BTY such that ATY is greater than or equal to C and Y is greater than or equal to 0. So that's to say you not only have pi I and alpha ij, but also because in the primal problem, there exist some orders of these inequalities, right? So they have some correspondence, and we can say that for pi I, they should correspond. Each pi I should correspond to bi in primal problem. Each pi I corresponds to the bi in the primal problem. And the alpha ij is about the arc. It should correspond to capacity constraints. In primal problem. In a primal problem. Right. So you should know that their correspondence. Pi I corresponds to bi, and alpha ij should correspond to the capacity constraints. That's about uij. Okay. Then how can we formulate this dual problem? By the duality formula, similar to that. So we can say that the dual problem is we want to maximize something. In the primal problem, we are minimizing zx, where z is some linear function, and the x is the flow on the arc. So in the dual problem, we introduce, because we have both pi and alpha here, so we introduce something called, say, w pi alpha, but never mind, that w is just some linear function. W pi alpha, we are maximizing it. So what is w? So according to the duality transformation, we can write it as sigma I in n bi pi I minus sigma I j in a uij times alpha ij. And for the constraints, it should be pi I minus pi j minus alpha ij is less than or equal to Cij for any ij in the arc set. And we also have alpha ij is greater than or equal to 0 for any ij in A. Right. So when this class is over, you can just try to yourself to transform from this to the dual. but I'm just writing down here. So alpha ij is greater than or equal to 0 for any ij in A. However, we should be noted that there's no restriction for pi I. Right. Be very careful. There's no restriction for pi. And now we have already formulated the dual for the MCF. Then we also introduce something called another definition. It is called reduced cost. Reduced cost of arc ij. But this may seem a little bit confused at first, but after we complete all this, you will understand why we introduce this. So what is the reduced cost? It is called Cij pi. So from this notation, you see that Cij is the cost. Cij pi is the cost, but this is in the case that we have already been given this pi, right? The node potential. So after we get some pi, after we get some node potential, we introduce this reduced cost definition. So Cij pi, it is calculated in this way. It's like Cij minus pi I plus pi j. All right. And a very natural question is, why do we need this? And the main reason is that we can eliminate the dual variables alpha ij using some properties of optimality. Okay, so that's very important. Why do we need this? Why do we need the Cij pi? And the main reason, I'll write it down. So we can eliminate alpha ij using some properties of optimality. This is the main reason why we introduce Cij pi here. Okay, so now that we have introduced the Cij pi, then there exists some very beautiful property for the Cij pi. So two properties for Cij pi. The first property. So we know that what is Cij pi? Cij pi is something like we have a node I here, we have node j here, and there's an arc between them. And Cij is given a priori. It's the unit cost of one of the flow on the arc ij. Then what is Cij pi? See, it is like Cij minus the node potential of the starting node plus the node potential of the ending node. So that's to say, for any cycle x, this is capital X, okay. For any cycle capital X in our network G, what can we say about sigma ij in X Cij pi? Anyone can tell me? What is this? What is this? So think about it. From I to J, and say J to W, and W to say Z, and Z goes back to I. So that's to say, when you are calculating Cij pi, you minus the potential of I plus the potential of J. When you are calculating Cjw pi, you minus the potential of J plus the potential of W. Then that's to say, they cancel each other, right? So this is just equal to, this is equal to sigma ij in x Cij. Right. Consider this example. Okay, so this is the first property. And the other property is for any path P. Let's say the path P from it goes from K to L. Okay. Then what can we say about Ij in P? Say Cij. What can we say about this? Similar to what we have derived here. So we can say that on this path, actually, it just minus the potential from the starting point plus the potential of the ending point. And for all the intermediate nodes, potential cancel each other. Because you plus for one time and minus for one time. So that's to say they cancel each other. Okay, so we can say that for any ij in the summation of ij in P Cij pi, this is equal to the summation of ij in P Cij minus pi k plus pi L. So remember that I said the path P goes from K to L. All right. Then okay. Then using this reduced cost, remember that in the dual MCF, for the constraints in dual MCF, remember that we need to have constraints pi I minus pi j minus alpha ij. That's equal to Cij, right? This is in the dual of MCF. Then this can be rewritten. It's rewritten as alpha ij greater than to minus Cij pi, right? Because we are replacing Cij minus pi I plus pi j by Cij pi. So this is equivalent to alpha ij greater than or equal to minus Cij pi. And also, since in the objective function of dual MCF, so remember that in the dual MCF, what is the objective function? The objective function is sigma I in n bi pi I minus sigma I j in a uij times alpha ij. Right, this is the objective function of the dual MCF. Then what do we observe? We observe that, because it's very important. So we observe that the coefficients of alpha ij is the coefficient of alpha ij is uij. It is minus uij, right? It is minus uij. And remember that uij is given originally because uij is the upper bound of the flow on arc ij. So uij is given a priori, and we can also say that, and we can also assume that uij is positive. It's a positive value. So we observe that the coefficient of alpha ij is minus uij. This is something that is less than 0. So, because since we are maximizing the dual, we are maximizing the dual. We are maximizing the dual, so that's to say we should always assign the least value to alpha ij. Is that correct? We always assign the least value of assign the least value to alpha ij in optimal solution. And remember that I said here, why do we need Cij pi? Because we can eliminate alpha ij using some properties of optimality. Then what is the property? The property is stated here. The property is that we can always assign the least value to alpha ij in the optimal solution. Then what can this tell us? What can this tell us? Continue with what I've written there. That's to say, in alpha ij, this is just a max of 0 and minus Cij pi. Think about it. So that's so we see that alpha ij is lower bounded by Cij, by minus Cij pi, right? This is in the context, this is in the assumption that pi is given. That's to say, for any node set of node potential pi, we calculate Cij pi. And for every alpha ij, it is bounded from below by minus Cij pi. So, and we also see that in the optimal solution, we want to assign the least value to alpha ij because the coefficient is always some negative constant. So that's to say alpha ij is max of 0, max between 0 and minus Cij pi. Is that clear? Zhang Rui, do you think it's clear?
Yeah.
Okay, sure. I just want to make sure that you have not got lost. Okay, I know that Thomas is very clear. Okay, all right. So alpha ij is max of 0 and minus Cij pi. Then for the dual, actually what we're doing is to maximize sigma I in n bi pi I minus sigma ij in A. And we replace this alpha ij by max between 0 and minus Cij pi times ij. Oh, this is what this is a very nice thing. So that's to say, we are given some feasible node potential pi. We are given some node potential pi, and the max between 0 and minus Cij pi is determined by pi. It is dependent on it's just calculated by pi. And this Uij is just given a priori. Then, i.e., the dual problem reduces to finding pi that optimizes. It reduces to finding pi that optimizes this guy. And as I said in the transformation, the pi is not does not have any restrictions. So this is a very nice property. So you could, although on the book the author didn't state this, but I think the reason why we do this is to transform from a constrained optimization to an unconstrained optimization, which is what we always desire, right? Let me see. Okay, and this is about the dual of MCF, and let's do a very quick review for weak and strong duality, because I say quick review because we have already covered this concepts in one previous section. All right, so let's do a quick review. I will not write the complete theorem of weak duality theorem. But let's just, I will just write down the keywords of weak duality theorem. So we have objective function, Zx. This is the objective function for the primal problem, and we want to minimize Zx. We want to minimize the cost flow. And we also have, this is for primal to minimize. This is for primal to minimize. And we also have objective function W pi alpha. This is for dual to maximize. This is to maximize. Then W pi alpha is less than or equal to Zx. If you don't remember the weak duality theorem, you can just review it because we have already covered it. And I think Dr. Costello should have talked a lot about weak duality and strong duality in her lecture. Okay, so that's to say the value of the objective function for the primal problem is always greater than or equal to the value of the objective function of the dual problem. We can first write something like this. This is the value for the primal problem, and we want to minimize it. And say this is the value of the dual problem. We want to maximize this. And another variable, and according to this, suppose we can find some pi alpha and x such that W pi alpha is equal to Zx. Then what can we conclude? We can say that this is the optimal solution, right? Because W is always lower bound for the Z. Okay, this is the weak duality. And what about the strong duality? So strong duality. So the strong duality is stated as for any choice of problem data. So when I say problem data, it means that's Uij, Cij, some value like this. The minimum cost flow problem, MCF, always has solution. The solution, let's say, is X star. And the dual has solution pi. And because we know that alpha ij can just be replaced by maximum of 0 and minus Cij pi, so we can just assume that the dual has solution pi such that Zx star equals to W pi. So that's to say the strong duality theorem tells us that the optimal solution always exists. Okay, and they are equal. Then by the weak and strong duality, by strong duality, we know that Zx this is equal to W pi. So sigma ij in A, Cij xij, this is the cost flow. This is just equal to sigma I in N, Bi pi I minus sigma I j in A. max 0 minus Cij pi times Uij. Right, this is what the strong duality theorem tells us. Then we can write it as sigma ij in A max 0 minus Cij pi times Uij. This is equal to sigma ij in A minus Cij pi times xij. So be very careful. This remains the same as this part, but for this part, you see that this is Cij pi, not Cij. So why can we get this from this? Well, you can just I think you can just expand the Cij pi by the definition. So we see that, so we know that Cij pi is Cij minus pi I plus pi j. So if you just expand this and cancel if necessary, I think you should be able to get this. Okay. So that's two things. Then the last important point in today's section. So we see that suppose this arc, let's suppose the cardinality of A is M. Let's just say we have M arcs in this graph. Then on the left hand side and the right hand side, we have M terms, right? On both sides, we have M terms. And also, both sides have M terms. Both sides have M terms. And we also know that the maximum of 0 minus Cij pi, this is definitely greater than or equal to minus Cij pi, right? Because we're taking maximum of 0 and minus Cij pi. And we also know that Uij, and we also know that Uij is greater than or equal to Xij. Wow. This also tells us something. That's to say, correspondingly, for each ij in the arc set, max of 0 and minus Cij pi is greater than or equal to minus Cij pi. And also Uij is greater than or equal to Xij. However, their summations are the same. What can we conclude? So this is just like is that clear? Thomas, can you tell us? If you take the summation, they are equal. And we know that this guy is always greater than or equal to this guy. And this Uij is always greater than or equal to Xij. However, their summation are the same. What can we say?
Still trying to figure out why their summations are the same.
Oh, first you don't need to care about this. This is derived from this. So, so if you want to derive that they are equal, you can just calculate by yourself after this class. But now I'm just asking, suppose we have this equality, and we know that these relationships, then what can we conclude? You just first you just take this equality as granted. Take it for granted. What can we say? Well, actually, this is very widely used in mathematics. So let's say, suppose we have I in some sets S, and we have AI times BI. This is equal to sigma I in some set S, CI times DI. And we know that, and also we know that for any I in S, AI is greater than or equal to CI, and BI is greater than or equal to DI. However, their summations are the same. So that's to say, we must have AI equals to CI, and BI equals to DI for any I. Right? They are equal. This is just a demo for this. So that's to say, So we must have maximum of 0 minus Cij pi, the maximum between them, times Uij. This is definitely equal to minus Cij pi times Xij for any ij. This is what we must have. Okay, then we can conclude something. Let me write it down here. Then we can say that the first thing that we can conclude is that Cij pi is greater than or equal to 0. Right? And the second conclusion we can draw is that 0 is less than Xij less than Uij. Oh, excuse me. Let me look at this. Seems that this is not easy to tell. Okay, so first we establish this, and I will encourage you to look at the textbook. And in the textbook, there's something called complementary slackness for Cij pi Xij or so. So you can refer to the textbook. And it seems that, sorry that I didn't make the note carefully here. You're right. So if you like, you can look at the contents about complementary slackness in the textbook after this part, because we have already introduced the equality relationship. Okay, so I think that's all for today. If you have any questions, just feel free to ask. Otherwise, we have finished. Thank you.
Explain why it is that we have that